Morning everybody. Today we're going to carry on some work with geometric series, and we're going to particularly look at something called sums to infinity. So what we're interested in today is if my sequence goes on forever and ever and ever, is there a case where geometric sequence goes on forever, that is there a case where the series settles on a value, or does it go off to infinity? It's quite an interesting question. One I always found interesting, especially at university, is a series is where you add an amount over and over and over again to something. Obviously some of them could be negative, but there could be sequences that are strictly positive, so every term's positive. You add something on every single time. However, despite the fact that you're adding something on over and over and over again, there is some limit to what value you can possibly get to. And that just seems a bit crazy to me, because it feels like if you're adding something on over and over and over again, you should just keep getting a bigger and bigger number. And it's to do with the way that limits work, and the fact that you are, despite you're adding something on more and more and more, it's the thing that gets smaller and smaller and smaller to the point where it gets so small it's not really making any difference whatsoever. So it's quite an interesting thing to think about. But let's just remind ourselves of what we did the other day, specifically when we briefly talked about convergent or divergent sequences. And so, first of all, or series even, sorry, we said that if the modulus of r is less than 1, in other words, r has to be between minus 1 and 1, then we get a convergent, or we get convergence. Otherwise, so in other words, if r is any other value apart from those possibilities, then we have divergence. What does that really mean? Convergence means settles on a value. And divergence means it doesn't. If you're going on to university to study mathematics, you'll get lots of this stuff about convergence and divergence. More about convergence, to be honest, because that's the thing that we define, and you get lots of arguments, including epsilons and other such business. You'll come across that in real analysis. If you're interested in looking it up now, type in limit of a sequence, and you'll find lots of fun stuff about it. Anyway, back to what we're meant to be doing now. So that's what we were talking about the other day. We said whether something is convergent or divergent, and so what we're going to now look at is thinking about if we make n tend to infinity, in other words, if we just keep letting n getting bigger and bigger and bigger, what happens to the sequence, and is there some formula for working out the value of a convergent sequence? So, obviously our formula, oops, Daisy, that's the wrong colour, for a geometric series is Sn equals a1 minus r to the n all over 1 minus r. Okay, so if r in modulus is less than 1, when we make n really big, we'll know we'll get some value at the end. So let's do that. Let's state that r is less than 1. Then Sn, actually is equal to a1 minus, actually let's expand this out, it's going to be simpler to see if we expand it out. A minus ar to the n, and we'll just separate the fractions up as well. So we've got a 1 minus r and arn 1 minus r. If you can't quite see where I've got that from, expand the top of this bit out here, and then remember you can separate the fraction up quite nicely. Or alternatively, put these back over a common denominator and factorise. They're the same thing, I promise. Okay, so if that's true, let's think about what happens in the limit. So if I take the limit, in other words, if I let n tend to infinity, you've seen this notation before when you've done differentiation. The limit of Sn is going to be the limit of this side. I can promise you that limits behave pretty well with algebraic operations. So I can do this. Again, if you're off to university, that's something you will need to show is true. And so now I can say to myself, okay, well, the limit of Sn, I'm just going to write as S infinity. That's just a notational thing, as opposed to anything particularly profound. And in my second bit here, as n tends to infinity, it doesn't change the fraction because n doesn't pop up anywhere. It's just a over r over 1 minus r. So that bit still stays the same. And on our last bit here, as n gets really big, well, if r is less than 1, then this top bit here tends towards 0. Because if n gets really big, r is less than 1, you're having something like, well, stick it in your calculator. If you put half in your calculator and times it by itself over and over and over again, you get closer and closer to 0. Because that's 0, the whole thing tends to 0. And so what we're left with is a nice formula, a nice neat formula for the sum to infinity of a geometric series. It's just a over 1 minus r. Okay, so let's have a quick look at the question. So I would suggest you guys having a quick go at this first. The first two bits you've done before, the third bit's just applying that formula. Once you've had a go at it, come back to the video and just check that you've got the right answers, and then some exercises to do today. So just pause the video now and have a quick go. So the sixth term of the sequence is going to be, we haven't done UN notation yet, so let's just do it like this. Sixth term is going to be AR to the n minus 1, which is 4 times half, and what the sixth term, so that's going to be to the power of 5, which ends up being a half times a half times a half. It's quicker to do on your calculator, but that should be 0.125, I think. Okay, let's have a look at part 2. Find the sum of the first 10 terms. Sn is equal to a 1 minus r to the n over 1 minus r. I want the 10th term, so I'm going to write S10 is equal to 4, 1 minus a half to the power of 10. I don't know that one. Actually, I think I do. I'll come back to that in a sec. Over 1 take away r, which is half. And if you bang that all into your calculator, you should get 7.992. Okay, part 3 says find the sum to infinity, so we need to use our formula, a over 1 minus r. We know it's convergent because r is half, which is less than 1. So that means we can say that it's going to be 4 over 1 minus a half, which is equal to 8. At this point it's really useful to compare these two numbers. You know the first and the fourth and the first number to a certain degree. You know the first number's 4. In this particular sequence, because we're timesing by a positive fraction, we know it's going to increase every time, the series. The sequence won't increase every time, but the series will increase. and after 10 terms I get to 7.992, and apparently sum to infinity is 8. So those things all sit well together. If you started at 4, you got 7.992, and then this answer was suddenly 7, you should be thinking, oh crikey, something's gone wrong here, and it's probably just an arithmetic slip, or you've typed something wrong into your calculator. So it's always worthwhile checking when you get to this point. So the questions I think you should do today: exercise 3E, question 1, 5, 7 to 11. Thanks very much guys, and I'll speak to you again tomorrow. Bye bye.